last class we discussed about electroabsorption modulators. Basically we discussed the principle of operation of an electroabsorption modulator, which is Franz-Kildish effect, and quantum confined Stark effect. Quantum confined Stark. Both these can be used to realize electroabsorption modulators. So, if you recall, the characteristic of Franz-Kildish effect is shifting of the absorption edge, red shift of the absorption edge of a semiconductor. So, if you have alpha, the loss coefficient in centimeter inverse versus the photon energy h nu, then normally the semiconductor may have a loss which goes like this, starting from Eg. Then in the presence of an applied electric field, this shifts. So, the latter one is in the presence of an electric field. So, just to distinguish, let me mark that graph. So, this is with E equal to 0, applied electric field equal to 0, and this is with applied electric field E of the order of 10 to the power of 5 volt per centimeter, 10 to the power of 5 volt per centimeter, that is 100 kV, 100 kV per centimeter. So, if you use the operating wavelength somewhere here, that is if you use a lambda OP or h nu OP, OP standing for operating, and corresponding to this there is a lambda OP. If you choose the wavelength such that you are here, then in the absence of the electric field, the absorption is very little. This is absorption. So, 10 to the power of 1 typical numbers, 10 to the power of 2, 10 to the power of 3, 10 to the power of 4, and so on, centimeter inverse. So, before application of the electric field, the absorption coefficient is very small, negligible here, but in the presence of an electric field, so you have an absorption coefficient which is here, which is significantly larger now. This is Franz-Kildish effect. In the case of quantum confined Stark effect, because of the step response of the absorption coefficient and because of the presence of excitonic peaks, the change is very large. So, in the absence of the electric field, you have a response which is like this, which shifts to in the presence of the electric field. So, this is with E equal to 0, and this is typically you need a lesser voltage here, lesser electric field. So, E of the order of 10 to 20 kilovolt per centimeter. Here you need of the order of 100 kilovolt per centimeter, here 10 to 20 kilovolt per centimeter. So, if you again choose lambda OP here, so this is h nu versus alpha, similar numbers, 10 to the power of, so 10 power 1, 10 power 2, 10 power 3, 10 power 4, centimeter inverse, and if you choose h nu operating or a nu operating or corresponding to that a lambda operating, such that you are located here in energy, then in the absence of the electric field, the attenuation coefficient here is negligibly small, and when you apply the electric field, attenuation coefficient jumps to a large value. So, the primary difference here is because of the quantum confined Stark effect. The primary difference is a large change in attenuation coefficient, and the peak here, excitonic peak, adds to it, because here there is no peak. So, typical delta alpha that you can get, delta alpha, which means delta alpha equal to alpha when E equal to 0. So, when E is in the presence of E minus alpha in the presence of E equal to 0, delta alpha, the change in attenuation coefficient is of the order of 10 to the power of 2 to 10 to the power of 3 centimeter inverse. Whereas, in this case delta alpha here is typically of the order of 10 to the power of 3 to 10 to the power of 4 centimeter inverse, about 10 times more. Otherwise, both of them refer to redshift of the absorption edge of a semiconductor. Absorption edge refers to the wavelength or the energy where the absorption coefficient suddenly starts shooting down. That is the absorption edge. So, redshift, shifting to lower energies or shifting to higher wavelengths. So, if you want to plot the same graph in terms of wavelength, it would have been the other way. So, you would have, so this is lambda, and then in the presence of an electric field it would shift like this. So, this is with E and this is with E equal to 0. So, red shift, shifting towards longer wavelengths. So, this is with E in the presence of E, and the lambda OP that I was talking is somewhere in between here, somewhere at the edge. So, lambda OP, because normally we talk in terms of operating wavelengths in optics and optoelectronics. So, this is Franz-Kildish effect and quantum confined Stark effect.
So, why does the excitonic peak reduce on application of electric field?
The question is, why does the excitonic peak reduce due to an application of the electric field? When you apply an electric field, as I had discussed in the last class, the wave functions associated with the electron and hole which forms the exciton tend to dissociate, that is, they tend to ionize. So, if you recall the quantum well structure here, a single quantum well, showing you a single quantum well, and there is the wave function here correspond, this is the lowest state, and you have a wave function corresponding to this state, and similarly you have a hole here corresponding to that, there is a wave function like this. You can show it inverted or this way, it does not matter. So, we have E1 and E1 dash. So, these are overlapping and they are holding together due to Coulombic attraction, and therefore, it forms an exciton. In the presence of an applied electric field, the well bends. So, in the presence of an applied electric field, the well takes this form. So, this after application of an electric field, there is a change in the energy E1, but more importantly, because of the applied electric field, the wave function becomes asymmetric and it tends to be located more to the other side, because there is a positive potential here, and therefore, the electron has an attractive potential to this end, which means in simple terms the electron wants to move to towards the positive end, which means the probability of locating the electron is more to this end, which means the wave function is more shifted to this end, and that is why the wave function becomes asymmetric. Here it is perfectly symmetric, but here it becomes asymmetric. Similarly, this wave function associated with the hole tends to move to the other end. Now, this tends to move they are not separated because the quantum confinement still blocks them. But the moment you have this one coming down, please see here, corresponding to this axis is energy, everywhere this vertical axis is energy, corresponding to this value of E, there is a state, and this electron of this energy can tunnel and go out, which means this electron has a probability to tunnel, which means there is a probability of dissociation, increased probability of dissociation, and therefore the excitonic peak goes down. It is just like increasing the temperature, the excitonic peak goes down. So, exactly like that, because the electron now has a probability to tunnel, the dissociation probability increases, and therefore the resonance peak goes down. This is why when you apply, in fact, if you apply stronger electric field, this completely gets dissociated and you will not see any peak. If you apply more stronger field, it will shift to this side. So, typically I would show this. So, you will have something like this, and if you apply further, there will be nothing for the higher electric fields. We do not want to go up to that, because we want, if the peak is present, then the step change delta alpha is larger. If the peak is not there, you see immediately now delta alpha is a little less. So, we would like to use the excitonic resonance peak. Today we will see how to apply. We talked of 20 kilovolt per centimeter, 10 kilovolt per centimeter, how to apply this electric field and what is the device configuration. So, we will discuss this today. First, let me discuss device based on quantum confined Stark effect. Early devices were based on this, but now there is another way of using a new configuration where you can use Franz-Kildish effect as well as QCSC. Both can be used independently. There was an early article in Physics Today. I would recommend you to read this article. This came in Physics Today, an article titled Quantum Wells for Photonics. By Daniel S. then Bell Labs. He was Daniel S. Chemla. This is a popular level article, May 1985, easy to understand, very old article, 25 years back, but still very nice and relevant. The concepts are given very nicely. Quantum Wells for Photonics, May 1985. Please see this article, it is quite nice. So, the question is how to apply a large electric field like 10 to the power of 5 volt per centimeter or 20 kilovolt per centimeter. So, E equal to 20 kilovolt per centimeter, 20 kilovolt per centimeter. So, this is equal to 2 into 10 to the power of 4 volt per centimeter, and 1 centimeter is 10 to the power of 4 microns. So, that is equal to 2 volt per micrometer. 20 kilovolt per centimeter is 2 volt per micrometer. Means if you can apply 2 volt across 1 micrometer. So, if this is 1 micrometer thick, if you can apply 2 volt across this, you are getting the field. So, it is not a big idea. So, it is not a very big number, provided you apply it across a small thickness. So, 2 volt per micrometer, this is the kind of electric field that is required. Now, if you take a quantum well, one quantum well, typically, please see the logic here, the width of the quantum well here is typically of the order of 100 angstroms, which means 10 nanometer, okay, typical width. Now, if I take this quantum well, which is 10 nanometer thick, so 10 nanometer, there is light incident here I in, then I out will be equal to I in into e to the power minus alpha into d, where d is the thickness d. Alpha is the absorption coefficient. Even if alpha is 10 to the power of 4 centimeter inverse, so this is I in into e to the power minus alpha, so 10 to the power of 4 centimeter inverse, and therefore, if I substitute d is equal to 1 micron, for example, if I substitute d is equal to 1 micron, then this will be equal to 10 to the power of minus 4 if d is for d is equal to 1 micron, for d is equal to 1 micron, this is equal to 10 to the power of minus 4, which is equal to e to the power of minus 1. I input into e power minus 1. Is that all right? And therefore, I out divided by I in is equal to e to the power minus 1, that is 1 by e. Normally, there is a parameter called extinction ratio. So, extinction ratio. Okay, I will discuss about this with the field and without field. I will discuss about this a little later. So, this is nothing but E is approximately 2.7, so approximately of this order, which means you see that I out has dropped down by a factor of about 3 or so. That is considering d equal to 1 micron. 1 micron is 1000 nanometers. If you take one quantum well, it is only 10 nanometer. So, we need at least 100 quantum wells to have 1 micron thickness, so that this ratio is significant. Please see, this is of the order of 0.33 or something like that. So, 0.35, 36, something like that. So, to have the output drop by this much, more than half, you need 1 micron, which means you need 100 quantum wells. Indeed, if you want to have significant attenuation, we had delta alpha equal to 10 to the power of 4 alpha centimeter inverse. So, even if the absorption changes by 10 to the power of 4, that multiplied by length of the device will give you total attenuation, and that total attenuation to be significant, you have to have at least 1 micron, which means you need 100 quantum wells. Indeed, the early devices, the first devices early in the 1980s, 1984, 1985 used quantum wells. One of the early experiments at Bell Labs used multiple quantum well structures, MQW structures. MQW structures, which means you have wells, barriers, wells, barriers. So, this is the well, and if they are non-interacting, then the energy remains the same and all the properties remain the same. So, typically well width D of the order of 100 angstroms and L the separation. So, this is L and this is D. We had taken a problem of the order of 100 angstroms, and about 50 to 100 periods, 50 to 100 periods. One period means one well and one barrier. One well, one barrier is one period. So, if I say that it is 100 angstroms width and 100 angstrom this, So, total is 200 angstroms, that is 20 nanometer. If I have 50 wells, so 20 if this is 50 periods, which means 50 into 20 nanometer, which is 1 micron. If you use 100 periods, then you will have 2 micron. So, the well width, the total well width, where attenuation, please remember attenuation is only here, outside there is no attenuation. Why there is no attenuation? Because the photon energy corresponds to this band edge. Outside, if I take a single quantum well, please see, we had E1 here, E1 dash here. The band edge corresponds to this energy gap. The band edge where the attenuation suddenly starts shooting up corresponds to this, and we have biased it just at the band edge. The input photon which is coming here, you recall in the principle that we discussed in the last class, light beam is passing through this and electric field is applied to the structure, and the output will be full or no output depending on whether you have applied electric field or not. This is the principle. But now we want to see with numbers real, what is the real device. If I have an h nu corresponding to this, outside it will not be absorbed because band gap is larger. Absorption takes place only in the well region. Therefore, if I have 100 periods, I have 100 wells of 10 nanometer, which means total thickness of the semiconductor where absorption takes place is only 1 micron, and therefore, this calculation that I have done, 1 micron 10 to the power of 4 is alpha, alpha into d applies for 100 wells. In other words, to have significant measurable attenuation, you need large number of quantum wells. Single quantum well will not do, but we are using property of a single quantum well, but to enhance the effect we have to use large number of wells. So, the structure that we have to use is MQW, multiple quantum well, multi quantum well structures or multiple quantum well structures. So, typically 50 to 100 periods are used. 1. I have still not told how to apply the electric field. First, I have said that we need, if you are going to use quantum confined Stark effect, we need at least 100 periods, 100 quantum wells to have significant effect. How to apply the electric field? We have to apply this much, which means 2 volt per micrometer. In electronics, we know a simpler idea, that is, if you take a p-n junction, we have already discussed this, p-n, then you know that there is a depletion region here, and from p side holes move to the other side. So, leaving behind negatively charged immobile ions and positively charged. So, there is field here, p-n junction. If you apply a reverse bias, so we apply a reverse bias, then this depletion region spreads further and the potential, built-in potential here becomes larger. Now, if you see the electric field, I just zoom this a little bit. We have already discussed this, how to calculate the electric field, because E of x is equal to integral rho x dx 1 by epsilon. Recall dE by dx is equal to rho by epsilon from Gauss law, del dot divergence of E is equal to rho by epsilon. From there, if you take one dimensional and if they are in the same direction, it is dE by dx, therefore, E is equal to this, which means if you are finding the electric field starts from here. So, it is negative. So, electric field increases linearly, and then as you add positive charges to the negative, electric field decreases and then it comes down here. So, what have I plotted? Electric field. Electric field versus distance. So, this is the electric field. Beyond this there is no electric field, which means the entire electric field is appearing across the depletion region. And what is the thickness that we have here? Typically the thickness of the depletion region is of the order of 1 micron or 2 micron. So, if you apply a reverse bias, then this field will, this may spread a little bit more. So, this will spread and you will have the electric field varying like this. What I have shown here is this is x versus electric field. This is width of the p region, many times we denote it as xp, and width of the n region xn in the depletion region, and this entire width is of the order of 1 micron. So, the point is the applied voltage 1 volt, 2 volt, 3 volt, whatever reverse bias that you are applying is appearing across the junction. The entire electric field is across the junction, and therefore, what is the electric field that we have here? This is of the order of 10 kilovolt per centimeter. It is 2 volt per micrometer, but it is 20 kilovolt per centimeter. So, if you using this concept, if you use a PIN structure, so what is the device configuration? Almost all devices use reverse biased PIN structure, reverse biased PIN. So, the structure looks like this. I will show you a better, so this is schematic representation. So, this is P side, N side, and this is the intrinsic region, which comprises of quantum well structures. So, the I here is MQW, the intrinsic region, and then you apply a reverse bias. So, PIN, the intrinsic region comprises of multiple quantum well structures, typically 50 to 100 periods. So, the entire, if you plot the electric field across this, how does it look? So, if you plot the electric field, the charges here will be negative and the charges here will be positive, and in the intrinsic region there is very little charges, and therefore, if you plot this, you will have electric field varying rapidly like this, and then in the intrinsic region, entire intrinsic region approximately constant, and then dropping down like this. This is at the junction P and intrinsic junction. This is at the N and intrinsic junction, and in the intrinsic junction the electric field remains almost constant. Electric field is equal to charge into dx integrated. So, you integrated all the negative charges here. So, the field increased up to that and hardly any charges here in the intrinsic region. So, the field is remaining constant. When you reach this end, the negative charge is compensated by positive charges. So, the sum is decreasing. So, the electric field is decreasing. In the case of a PN junction, we had the electric field variation like this. In the case of a PIN, the electric field almost remains constant. There could be little bit slope depending on which P side is more doped or N side is more doped, but almost constant. Remember that this axis is electric field. So, we have a uniform electric field of the order of 10 to the power of 5 volt per centimeter applied to the intrinsic region. And what is the thickness of this intrinsic region? Is just about 1 micron or 1 to 2 micron, 100 quantum wells. 2 micron is the total thickness of this. So, we are able to apply a large electric field at the junction region. So, this is the device configuration which is used. A practical device looks like this is a schematic illustration. A practical device looks like, let me show you a practical device how it looks like. So, you start with a gallium arsenide substrate. This is, you see the procedure is also illustrated here, gallium arsenide. On this you deposit aluminum gallium arsenide. On this, by deposition and etching, you grow multi quantum well structures. First start with N gallium arsenide. So, N gallium arsenide substrate. On this you deposit N aluminum gallium arsenide, and then you deposit the multi quantum well structure MQW here. This MQW comprises of gallium arsenide, aluminum gallium arsenide, Al 0.3, Ga 0.7 arsenic MQW structure. Over that you have P type aluminum gallium arsenide, and over that the metal electrode. Now, the substrate is etched from the back side till you reach. So, this portion is etched away, and then etched away means the material here is etched. It will become clear why that is done. So, this is the substrate, and then you deposit annular electrode. I could have shown you the structure directly, but I just wanted to illustrate the procedure also. So, a substrate on which epitaxially these layers are deposited, and then this is etched away, and an annular electrode. Annular means, why annular electrode is required? Because light enters from here. So, this is the path of the light beam. Please see the structure. Here you apply, this is the negative electrode. So, N, and therefore, you have to apply positive. This slot, this vacant slot is for light to pass through. This is gallium arsenide, aluminum gallium arsenide quantum well. This is for operation around 800 nanometer, lambda operation around 800 nanometer, because the material is gallium arsenide, aluminum gallium arsenide. The band gap is about 1.42 for gallium arsenide. So, 1.44, 1.45 will give you approximately 800 nanometer as the lambda operating wavelength. I hope it is clear. You recall that if you had H nu here, for gallium arsenide bulk it was here, this is 1.42, and then for the quantum well it was here. So, this may be about 1.46 eV. So, your operating voltage has to be somewhere here, say H nu OP is 1.45 eV, which means lambda operating is equal to 1.24 divided by 1.45 micrometers. That is about 800 nanometers, 0.8 micrometers, approximately around that region, because I have used gallium arsenide. If you want to use the electro-absorption modulator for optical communication, it will be based on indium phosphide substrate and indium gallium arsenide quantum wells. Indium gallium arsenide phosphide, the quaternary compound is used. Is this picture clear? That this is N on which intrinsic gas gas layers which are quantum wells. This is P aluminum gallium arsenide. Please note that we have etched this so that the gallium arsenide does not reabsorb this. When this peak is shifted here, gallium arsenide could absorb the light. Light is coming at 800 nanometer. So, gallium arsenide would absorb it. 800 nanometer is somewhere here. So, absorption coefficient is large. So, to avoid absorption by these gallium arsenide regions, it has been etched off. Whereas, the region here is aluminum gallium arsenide, the region here is aluminum gallium arsenide, they do not absorb because they have a larger band gap. Aluminum gallium arsenide has a larger band gap compared to gallium arsenide. So, this is the early structure of electro-absorption modulator based on quantum confined Stark effect. Typical dimension here. So, this is substrate. So, typically about 100 micron, 60 to 100 micron, and this slot which is kept open is also typically this slot, and the slot here is 50 to 100 micrometer. And this thickness of the MQW is of the order of 1 to 2 micrometer as discussed in the principle, and it is a reverse biased PIN structure. So, PIN, this is PL gas, NL gas and PIN structure and reverse bias. This is the device configuration. But today there are better device configurations, because one of the important restriction that we have is 1 micron, 2 micron, you have to write 100 periods. The periods have to be identical. If the periods are not identical, the energy is different, and then the effect will be different. It is not enhanced, it will start broadening, and therefore an easier and more better. Please see, the extinction, the difference is given by minus delta alpha into L. What is this delta alpha? Please see, I output with E equal to 0 is equal to I in into e to the power minus alpha with E equal to 0 into L. When there is no applied electric field, I have this device. I do not know what is this device. This is electro absorption modulator. There is an input which is I in, there is an output I out. I out with E equal to 0 is I in into e to the power of alpha is the attenuation coefficient without any electric field. You are applying an electric field from here. Let us say this is E field. In the presence of electric field, I out with E equal to I in into e to the power minus alpha into E is not equal to 0 into L. E is maybe 10 kilovolt per centimeter, 20 kilovolt per centimeter, whatever. E is the operating. So, let me put EOP, okay, operating electric field, EOP. This is the output when there is no applied electric field, and this is the output when there is electric field. So, what is modulation? Modulation is the ratio between these two in the presence of electric field and in the absence of the electric field. Modulation is you are modulating the output intensity based on the applied electric field. Modulation means what? So, you are applying an electric digital pattern electric field to this, and you are seeing how light is modulated. So, modulation ratio the modulation index is given by, which is also called the extinction ratio in this case. So, the extinction ratio ER is equal to I out with electric field divided by I in without electric field, I out without electric field. In is constant, I out without electric field. So, this is the extinction ratio, and that is equal to I in cancels. So, we have e to the power minus alpha with e equal to 0 minus alpha with e operating into L. So, let me erase this structure. I want to discuss a new structure into L. This is what I had written as delta alpha. So, this is equal to e to the power minus delta alpha. Delta alpha is the change in attenuation coefficient because of the applied electric field. This was without the field, this is with the applied field. So, change in attenuation coefficient into L. And this change, what is the point to see? Extinction ratio or equivalent to modulation index, the modulation, the difference between in the presence of electric field and in the absence of electric field depends on the product delta alpha into L. One is, if I have a large delta alpha, that would be wonderful. That is why we said quantum confined Stark effect is better than Franz-Kildish effect, because the change in alpha is much larger in the case of QCSC. However, I have a second parameter L. Suppose I make L large, then I can use even Franz-Kildish effect. It is not necessary that I should go to, because it is the product which will determine the extinction ratio, and hence the new design, currently it is the waveguide modulator design which is used. So, this is the extinction ratio, which clearly tells that it depends on the product of delta alpha. Delta alpha is the change in attenuation coefficient due to the applied field multiplied by the length of the device. So, the current devices are, let me show you first the 3D picture. It is much easier to fabricate and much easier to realize. So, I will first show you the structure and then I will explain what the structure is. Okay, let me make it 3D. So, this is actually ridge waveguide structure. So, you have the substrate, let us say N indium phosphide. Let me draw, say now indium phosphide. All the while I am writing gallium arsenide, let me write indium phosphide. Okay. And here is this is the substrate, and this is I indium gallium arsenide phosphide for communication wavelength. Just to distinguish this internal layer, I will mark it with the dotted lines. So, this is N type. So, N indium phosphide. Okay, let me draw it. N indium phosphide. It could be some other material also, and this is P indium phosphide, and on top is the metal. This is the contact, and at the bottom there is a contact. Let me draw the structure and then we will discuss. So, what I have drawn is extinction ratio is equal to extinction ratio is equal to this. What I have drawn is a ridge waveguide. If I show you only the front end, it will be like this. This is the contact, this is the bottom contact, and here is the, so this is indium phosphide and this is indium gallium arsenide. This is a ridge waveguide, it is called a ridge waveguide structure. I will explain what I mean by that. If I show the longitudinal cross section, it will look like this. This is the transverse cross section, the end that you are seeing, and if I show the longitudinal cross section, it will look like this. One-to-one correspondence. See, this is the same as this, this is the same as this, this is the substrate. So, this is longitudinal cross section. I hope you follow longitudinal cross section like this, and the other one is this. So, this slice is like this and this slice is like this, longitudinal cross section. So, one-to-one. So, this is indium phosphide. Light is launched into this structure. So, let me show a lens and light launched into this here, this structure. This indium gallium arsenide phosphide forms an optical waveguide. What is an optical waveguide? A high index layer sandwiched between two low index material, the guiding film and cladding. Outside is the cladding. Indium phosphide has a lower refractive index, it has a higher band gap, therefore, a lower refractive index compared to indium gallium arsenide phosphide. This has a higher refractive index, therefore, this structure is an optical waveguide. So, here it is. So, it is propagating in this direction, and the thickness of this layer here, guiding layer, this is D, typically 0.1 to 0.5 micrometer, and the length here, so this is longitudinal, this is transverse cross section. So, L, the length here of the waveguide L is typically 50 micron to 200 micrometer. I have a 0.2 or 0.3 micron thick optical waveguide, the thickness, and then this is, as you can see there, this is N, this is P, upper one is P. This structure, similar structure we will see for laser diode, but laser diode, which is a double hetero structure, laser diode is operated in forward bias. Here our objective is to apply a reverse bias across the intrinsic region. So, if we apply a reverse bias here, so this one is negative, so I apply a negative bias and this one is positive, okay. So, reverse bias, then across the intrinsic region here you have the same field. What did I gain by this structure is L. Earlier my L was just 100 quantum wells I had, and the thickness was only 1 micron or 2 micron was L. Now L is 50 to 200 micrometer. Therefore, I do not even need any quantum well structure. This is not quantum confined Stark effect. This is based on Franz-Kildish effect. I apply an electric field, the absorption of this region shifts, the change is small, delta alpha now will be 10 to the power of 3, not 10 power 4. Delta alpha is small, but my L is not 1 micron, 100 micron. So, we can realize the same extinction ratio even by Franz-Kildish effect under this configuration. This is called waveguide configuration of electroabsorption modulator. Waveguide configuration of EAM, electroabsorption modulator. So, the structure looks like this. It is a ridge, elevated ridge. We make a ridge because we want a beam to be confined. It is not, otherwise if you do only this, it will become planar waveguide, and that is why we have made a ridge, so that if you see the optical mode, optical energy will be confined here like this. So, it is a ridge which is carrying light. So, this is the optical mode. One last point is the alpha that you have, the attenuation coefficient alpha effective will be equal to alpha A into gamma. Alpha A is the actual absorption coefficient of the material which we shift. Alpha effective equal to alpha A into gamma, where gamma is, in laser physics this is called confinement factor or overlap factor, confinement factor. When you launch light of some intensity I, note that because of the optical mode, a fraction of the energy is outside this layer, not the entire energy is seeing alpha A. Alpha A is the attenuation coefficient, actual absorption coefficient of the material, but the entire energy is not seeing this alpha A. A fraction is outside. The outside fraction does not see any absorption coefficient, because the material outside is a higher band gap material that is not absorbing, and therefore, the actual effective alpha, you have to substitute here effective alpha to calculate the real extinction ratio. Typically, this gamma is anywhere from 0.5 to 0.9. So, it is not very small, but a correction factor need to be applied to take care that now you have an optical mode. In the earlier structure, I showed you a beam passing through that quantum band. It was not a mode, but now it is an optical mode, and therefore, a correction factor gamma is required. This gamma is less than 1. So, gamma is less than 1. Typically 0.6, 0.7, 0.8, 0.6 to 0.9 is the gamma. Please see, the thickness is very small, 0.2 micrometer, and therefore, even if you apply 1 volt, 2 volt, you get 20 kilovolt per centimeter electric field. So, all switching voltages required are only few volt, 1 to 2 volt is the typical. Today commercial devices are available, and just 1 to 2 volt of switching volt for electro absorption modulators. We will discuss the actual structure a little later when I discuss about laser packages. These come in butterfly packages, what are called 14-pin butterfly packages. We will discuss and how the device actually looks like. It looks like a small IC, a very small IC. We will stop here.